Okay, good morning and welcome back. It's 11 o'clock. Let's get on to work. Before we start, please, do you have any questions for me? Any comments or any concerns? Okay, so as you all know, Friday we have our second exam, right? I sent you an email and that one has like all the instructions on it. I've solved the study guide problems, right? And I posted it on Canvas, right? So it's there. Math Center will also be there to do like a math review. So please make sure you use all of those to help you, right? Prepare for the exam. One other thing is on Wednesday is no instruction day. So unlike the reading day where I could make a video, for the no instruction day, I'm not going to make any video, right? I'm not going to instruct, right? So no instruction, so no video, nothing. So that means that after today, I'll be seeing you on Friday, right? Yeah, so that's it on that one. Please, any questions on this? Okay, then let's get on to work. So last time, right, I'm sharing my screen. I'm sharing a PowerPoint slide. If you can't see, do let me know. So the last time we were looking at related rates. And then we said that sometimes some objects change with respect to time. And then it might be difficult or impossible to measure them, right? But then if you are able to relate them to another rate, which also changes with respect to time, then that one happens to be easier to obtain, then you can use the related rates idea to obtain the rate for the unknown, right? So we discussed this and then we were looking at the first example, right? So we are saying air is being pumped into a spherical balloon so that its volume increases at a rate of what? 100 centimeter cube per second. How fast is the radius of the balloon increasing when the diameter is 50 centimeters? So for this one, just as with any story problem, right? Any word problem, you have to be able to obtain the mathematical notations from the words, right? So looking at this first thing that we are being told here, we are told the volume increases at a rate of what? 100 centimeter cube per second, right? So if I let V be equal to the volume, I let my R equal to the radius, right? Now, this information that you have here is volume increases at a rate of 100 centimeter cube per second. So that tells you that that is dV over dt. We know we are changing with respect to time because it is per second, right? And it's volume, so centimeter cube over time, right? So dV over dt is 100 centimeter cube per second. Well, let's continue reading this. How fast is the radius of the balloon increasing when the diameter is what? Is 50 centimeters. So the question is asking for how far the radius is increasing. So that means that the problem is asking for the R over dt, right? And then we are told that the diameter of this spherical balloon at the time where it's 50 centimeters. So how fast is the radius changing or increasing, right? When the diameter is 50 centimeters. So we've been able to obtain the information from the problem. Now, one other important thing is we know that this is a spherical balloon, right? So we have a spherical balloon, and then we are giving information about the change in volume, right, with respect to time. So the thing is, you have information for this, dV over dt, but you are asked to find the R over dt, and then the air is being pumped into a spherical balloon. So because we know the dV over dt, and we are asked to find the R over dt, we need to think about an equation which relates volume and what? And radius. And in this case, since it's a spherical balloon, then we're looking at what? A relation which relates what? Volume and the radius of a spherical balloon. So the go-to will be to try and find the volume of a sphere in terms of radius, right? So the volume of a sphere is given by V equal to 4 over 3 pi r cubed. That's the volume of a sphere. Now you see that with this equation, I have the volume in there and I have the radius, right? I have volume and I have the radius. So all that I have to do here is, since I'm asked to find the radius, the rate of change of the radius with respect to time, and I have an equation which has the volume and the radius in it, I'll just do d over dt of both sides, and then everything will play out, right? So I have the information here. Let me go to the whiteboard. Since the solution is already here, let me go to the whiteboard so that we solve this together. So example 1, we are given dv over dt to be equal to what? 100 centimeter cube per second. And then we are asked to find the r over dt, right? And then diameter is 50. Now, the equation that we said relates the volume and then the radius is given by volume of a sphere, which is 4/3 pi r cube. Okay, and then the question is asking for dr over dt. So what we do is just do d over dt of both sides. So that'll be dv over dt equal to d over dt of 4/3 pi r cube. And then when you get here, just try and use the differentiation rules, right? So dv over dt is just dv over dt. And then for this side, the 4/3 pi, we can pull it out by the constant multiple rule. Then we have d over dt of r cube. Now, when you get here, ask yourself, for this d over dt of r cube, as you can see, when you blow air into a balloon, right, then you know that the radius is changing with respect to time. So that means the radius is a function of time, right? So say, after I say 2 seconds, maybe the balloon is like so. After I say 5 seconds, it's like so. The radius is changing. You see? So the radius is a function of time. So in this case, for this example, the dr cube over dt, for that one, I know r is a function of t. The radius is a function of time as we blow air into the spherical balloon. So that means for that one, the derivative of this with respect to time, we will have to use the what? The chain rule, right? You have to use the chain rule because the r is a function of time, right? So we have our inner to be what? Our r, and then our outer is 3 because the r is a function of time, right? It's a function of time. So that means for that side, we have 4/3 pi, and then this one, differentiate the outer function, 3, plug in the inner function, right? And then 3r squared, and then multiply by what? The derivative of the inner function. So that'll be this. Right, so simplifying matters. You have dv over dt. Simplifying the equation, you have dv over dt equal to 4/3. The theories will cancel out, so I have 4 pi r squared dr over dt. But then the question is asking for dr over dt, so I'll just divide both sides by 4 pi r squared. So that'll give me 1/4 pi r squared, and then dv over dt equal to dr over dt. So with this equation, I can now find out dr over dt, right? But then what's dv over dt? It's just 100, right? So that'll be, but wait, before we do that, we need a radius, right? We need a radius. It's r squared here. And then we can get the radius from the diameter, right? The radius, because the diameter is 50, the radius will be 50 divided by 2, which is 25 centimeters, right? So putting everything together, we have dr over dt equal to 1/4 pi, and then 25 squared, and then dv over dt, which is 100 centimeter cube per second. So I have 100. Yeah, I have 100. Yeah, like so. Right. Now for this one, the unit will be, the radius is in centimeters, the time is in seconds. So this will be centimeters per second. Right. So let's simplify this. I'll have, I think 4 cancels this. 4 times 1 over 25 will be 100. So that'll leave us with, I think, 1/25 pi. Right. Centimeters per second. That's the r over dt. Please, are you okay with this? Any questions on this solution? Yeah. So in sum, right, first pick out the information from the word problem. Try and see if you're given, say, something changing with respect to time. Write all of those down. And then ask yourself, what am I asked to find? Now, check what you're given, the rates that you're given, and then look at what you're asked to find and try and find an equation which will relate the two, right? And then when you get that equation, then you set everything up. You do d over dt of both sides. Everything will be set up. But always be cautious, right? Some of the variables may be changing with respect to time. And if they change with respect to time, consider them as functions of time. For example, for this case, for the spherical balloon, the r is a function of time, right? So we have to do what? Chain rule. Now, if it's not a function of time, if it's always constant, then you will treat it as a constant, right? And I provided an example which will show this, which will illustrate another case where the r is constant. Please, any questions here? Okay. Anybody needs time here? Okay, then let's go back here. Okay, so this is just nice notes. It talks a lot more about what is happening, right? And then it solves everything. And then we get this, right? And it has an approximate value. Okay, now let's look at this other question. For example, 2, a cylindrical tank with radius 4 meters is being filled with water at a rate of what? 2 meter cube per minute. And then how fast is the height of the water increasing in meters per minute, right? Okay, so now for this cylindrical tank, right, let me just do a quick sketch here, something like so. And maybe blue. Okay, so this is what you have, right? Water is being filled in there. Okay, so now for this one, right, we are asked to find how fast the height of the water is increasing. Now, don't forget that water takes the shape of the object that you pour it into, right? So if water is being put in a cylindrical tank, then the shape of the water will also be cylindrical, right? So that's the first thing. Now, the next thing is, let's try and get the information from the problem. So a cylindrical tank with radius 4. So radius, R is radius, is equal to 4 meters. It's being filled with water at a rate of this. So as you can see, if it's being filled with water at this rate, then that's the volume, right? The volume is changing at 2 meter cube per minute. So volume, so if V is volume, then the V over the T is equal to what? 2 meter cube per minute. Okay, how fast is the height of the water increasing in meters per minute? Okay, so how fast is the height? That means that the question is asking for what? The H over the T, right? I'm letting H be my height. Height of water. Height of water. Okay, so I have this, right? So now, let me try and get a relation, right? So the thing is, I'm giving the V over the T, right? And I need the H over the T. So what you think about is, can I get an equation which relates the volume and then the height, and it involves a cylinder? Well, that's essentially just trying to find the volume of the cylinder, right? And what's the volume of a cylinder? The volume of a cylinder is just pi r squared h, right? It's just pi r squared h. Okay, so now that we have this equation which relates them, right, then you just need dv over you do d over dt of both sides, right? So you do d over dt with respect to time, and this d over dt and pi r squared h. Now the left hand side is still dv over dt. Now for this side, the pi is a constant, we can pull it out. But the question is r changing with respect to time? Is r a function of time? Can anyone help me with that? Is r a function of time? The radius of the water, is it a function of time? I see something in the chat. Perfect.
No.
Thank you, Megan. Yeah, it's not a function of time. No matter how the water is increasing, the radius stays the same. The radius of the water, it stays the same. It's not a function of time. The height, however, is a function of time, because maybe at time 2, the water has been filled to this level. I say time 5, it has filled. So it's changing with respect to time. However, the radius is still the same. You see, that means that in this case, the radius is not a function of time. So you treat it like a constant. So in this case, the pi and r squared are all constant. So I'll just pull them out. So I have pi r squared h over the t. Now the h is changing with respect to time. So that one is just gh over the t. Please, I hope you get this. Okay, now when we get here, we just try and solve for the h over the t. So anybody needs time here, I'll need to move on to the next slide. Okay, so that means that the v over the t equal to pi r squared the h over the t, right? So if I'm solving for the h over the t, then the h over the t will just be equal to 1 over pi r squared and then the v over the t. Now let me see the information that I'm given and then try and put everything together. So the radius is 4. So that means this will become the h over the t will become 1 over pi, radius is 4 squared, and then dv over dt, what is that one? That's 2, right? So that's 2. So when you get here, you can just simplify. So that will give us, that's 2 over pi 16 pi. Okay, let me just say pi times 16, right? And then the unit is what? Meters per minute, right? So finally, the h over the t, you can simplify this a bit. I get, that's 8, right? So 1 over 8 pi meters per minute. Please, I hope you get this. Any questions? So that's it on related rates. The homework too is about just 5 questions. So yeah. Any questions here? That's it for 3.9. Yeah, so one thing is for 3.9, you see that you need to know some formulas, right? Of like solid figures and volumes and stuff. That one, no one is going to give it to you. You need to know them, right? For example, if someone asks you about the surface area of a sphere, the surface area of a sphere, then you have to know that the surface area of a sphere is 4 pi r squared, and so on and so forth. So you have to know that part of the equation derivation. Yeah. And that's all on this. Anybody needs time here? Any questions on related rates? Okay, Taylor. Yeah, let me wait for you. The child is behaving weirdly today. It just doesn't stay at one place. Okay, Taylor, you're welcome. Okay, then let's go on to 3.10. 3.10. Save. Oh, wait, I see something in the chat. Yeah, related rates will be on the exam. And for that one, I'll encourage you to do like the homework, solve the questions in the homework. There are just 5 problems, so shouldn't be too bad. Okay, so I'm sharing the PowerPoint slide for 3.10, and that's linear approximations and differentials. Linear approximations and differentials. Okay, now, do you recall that we said that at the point of tangency, right? At the point of tangency, the tangent line is very, very close to the curve, right? Well, at the point of tangency, they are the same. They are the same point. But in close, in the neighborhood of the tangency, right? The curve, the tangent line is very, very close, right, to the curve. So the thing is, this section is about approximation. So sometimes we may be interested in actually finding the value of the function at, say, points around the tangency. But sometimes it may be impossible or even very difficult to solve them, right? So if it's very difficult to do it, then because the tangent line is very, very close to the curve at the point of tangency, then that means we can use the value on the tangent line to serve as an approximation for the value on the actual curve, right? So that's what linear approximations are about, right? So this is a sketch which is showing us what is happening. As you can see, this is the point of tangency, right? This is the point of tangency. Now, at this point, in the neighborhood, very, very close, you see that this tangent line, which is in red, is very, very close to the blue line, which is the actual curve. So if, say, I want to find the value of the function and say a point here, then instead of using the value on the actual curve, I can approximate it using the value on this tangent on this tangent line, right? Because they are close in that region. You see, so that's the idea of linear approximations, right? So as you can see, at the point of tangency, they are the same values. But in the neighborhood, right, the closer you are to the point of tangency, the better your approximation is, right? And the reason why we use linear approximations is linear functions are easy to evaluate. They are very, very easy to evaluate, right? That's why we do this. Okay, so that's the concept. So essentially, we are not doing anything new. All that we are doing is we are just finding the equation of the tangent line and then reading the values on the equation of the tangent line to approximate the values on the actual curve. That's what we are doing. So it's nothing new, right? But we are just calling it linear approximations. We are just using the tangent line instead of the actual curve to approximate the values. So let's see how this is going to work. So essentially, you are just going to find the equation of the tangent line, nothing new, right? So if you have the point A, f of A, right, and you're looking at the tangent line at that point, then the equation of the tangent line is just going to be what? Don't forget it's y minus y1 equal to mx minus x1, right? And then our y1 is f of a. And then our slope, we just learned that the slope is or the derivative evaluated at a, the slope of the tangent, and then this s minus a. So when you rearrange everything, you're getting y equal to what? F of a plus what? F prime of a, and then x minus a, right? So that's how they are getting this. Now, what we are saying is the actual curve, which is f of x, can be approximated using this what? This tangent line. So that's why you see f of x is approximately equal to what? This f of a plus f prime of a into x minus a, which is the same as the tangent line, right? So this is called a linear approximation or tangent line approximation of f at a. So whenever you want to find a value, all that we need to figure out is just find the x value that you want to evaluate and plug it in there. But as I said, your approximation will be very good if you are close to the point of tangency. If you move very, very far from the point of tangency, then as you can see from this graph, right, as you move far, say if you consider this a point here, then the curve and then the tangent line are very, very different. You see, the values on the two are not close. But if you look at close to the point of tangency, then they are not too distinguishable. You see, they are very, very, very close. So that means that this will be a good approximation, right? Please, any questions on the concept? Okay, so then let's move on. So all that we're doing is we are now going to call the tangent line, instead of using the y, we're just going to replace with the L of x. So we'll call this a linearization of the function at a. But as I said, it's nothing new. It's the same as the equation of the tangent line, right? The y had just been replaced with L of x, right? From here, this y has been replaced with L of x, right? So it's the equation of the tangent line, nothing new, right? So if the question asks you to find the linearization of a function at a, you are basically finding the equation of the tangent line at a, and then just replacing the y with L of x. And then don't forget that the function itself is approximately equal to the L of x. That's all. Okay. So please, any questions here? Anybody needs time? Okay, then let's look at this. So let's look at the first example. Now the solution is on the PowerPoint. So let me go to the whiteboard and then try and work this out. So this 3.10 linear approximations and differentials. So we have example 1 on slide. Oh, by the way, I'm sharing the whiteboard. If you can't see, do let me know. Example 1. So we have f of x equal to square root of s plus 3. And we are looking at the linearization at a equal to 1. And we said use it to approximate square root of 3.98 and square root of 4.05. Okay, so we have this, right? Another follow-up will be whether they are overestimate or underestimate, but we talk about that on a PowerPoint. So let's look at this. And you get a question like this on your exam. I'll give you a function and ask you to linearize, right? In other words, find the equation of the tangent line and then use it to find what? Approximate the value, right? So this is the last concept that you have to learn going into the exam. Okay, so we say, okay, let's try and linearize, right? Let's find a linearization. So we know that the linearization is what? It's just the equation of the tangent line, right? We call it L of x, and it's what? The function evaluated at a plus what? The slope of the tangent, then s minus a, right? So in order to get f of a, I think we already have f of x. So f of a, in this case, our a is 1. It's just f of 1. So that just be equal to square root of 1 plus 3, which is 2. And then in order to get f prime of a, which is the f prime of 1, we need to get f prime of x, right? So to get f prime of x, we do d over dx of what? Of square root of s plus 3, right? So that's d over dx of s plus 3 to the half. And then for this one, as you can see, this is a composite function where our inner is s plus 3, and then our outer is a power function, right? So that means that the f prime will be equal to what? So this one, differentiate the outer function, which is a power function. So half, plug in the inner function, s plus 3. And because it's a power function, you have to subtract 1 times the derivative of what? The inner, s plus 3. So f prime is just going to be, so we have half, and then s plus 3, and then this negative half, and then this is just 1, right? So now that I have f prime of x, I can obtain what? The value at a, right? So I can get f prime of a, which is f prime of 1, right? So that'll just be half, then I have 1 plus 3, and then to the negative half, then times 1. And that's just going to be, so 1 plus 3 is 4, right? And then I have 1 over 2, and then this one will just be 4 to the half. So that just give me 1 over 4, right? Because 4 to the half is the square root of 4, which is 2. 2 times 2 is 4. So now I have f prime of a, right? So now that I have the f of a and f prime of a, I'm ready to get a linearization, right? So the linearization of f of x at a is given by, so we have, you just write your L of x equal to f prime, f of a, what's that, 2, and then plus f prime, so that's half, 1 over 4, sorry, and then x minus a, s minus a is 1, right? So like so. Then when you get here, we can just simplify. Yeah, but please, do you have any questions up to this point? Okay. Anybody needs time here? Okay, now let me get the L of x, the linearization. So that means L of x equal to, so I have 2, and then this s over 4, 2 plus x over 4, and then minus 1 over 4. So L of x is equal to 2 minus that will give us 7 over 4. So that's 7 over 4 plus x over 4. So that's the linearization. So on your exam, I'll first ask you to get this linearization. As I said, it's nothing new. It's just the same as the equation of the tangent line at that a. No, nothing new, right? Okay, so there's the linearization, right? Now, after obtaining the linearization, let's use this to approximate the values that we are given. Now, with this linearization that we have, we are saying that square root of what? S plus 3, which is the original function, square root of s plus 3, is approximately equal to this 7 over 4 plus x over 4. It's approximately equal to this. So if you're given something like square root of 3.98, now if I just asked you right off the bat to give me the square root of 3.98, you probably say you can't figure this out without a calculator. But at least for linearization, you can at least guess, you can work it out. This one, the square root of 3.98, you can't work it out. But for linearization, you can at least work it out. Right, so we know that square root of 3.98 will be approximately equal to what? So we just need to figure out the x, right? So if the structure is square root of s plus 3, right, and we need the x, then all that we can do here is what? Is just set this 3.98 to be equal to s plus 3 so that we can get the x and plug it in here, right? So with this one, you get s equal to 3.98 minus 3, so x equal to 0.98. So that is the x we are trying to find, right? So just plus 0.98 over 4, right? So that means this square root of 3.98 is approximately equal to this. And then you can get the actual value, right? You can do your computations and get this. So that'll be approximately equal to, let me get the answer from here. I think it's 1.995. Approximately equal to 1.995. And if you are curious, 1.995. And if you are curious, you can actually point this in your calculator. You see that it's quite close to this value, right? You see that it's quite close. So that means this is approximated as this, right? Okay, now let's do it for the other one. Please, any questions here? Is there any part you don't understand that you want me to go over? Okay, then let's do square root of 4.05. Is this 0.5 or 0.2? 0.5, yeah, 0.5. Okay, so for this one too, just as we did for this, we know that this is approximately equal to the linearization, right? So that's 7 over 4. And we need to figure out the x that we have to plug it in here, right? So to do that, let's look at the original structure. It's square root of s plus 3, right? So let's figure out the x from this part, right? So that means we just have to set 4.05 equal to s plus 3 so that we get the x, right? So you get x equal to 4.05 minus 3. So s is equal to 1.05, right? And then when you get it here, you just plug it in there. So that'll be 1.05 over 4. And then with this one, you can just get your answer to be 2.0125. So that's approximately 2.0125. So that's how you approximate. And you see that if you actually punch this in your calculator, you get it to be quite close to this value. Right. So that's the power of linearization. Please, any questions here? And as I said, you get a question like this. You solve the linearization and then you have to approximate one value. Right? You have to use it and approximate. And that's how you're going to do it. Okay. Please, anybody needs time here? Okay. Then let me go to the PowerPoint if you guys are okay here. So PowerPoint. Okay, so this is just going to give us nice notes. I mean, we actually worked everything out, right? And the last part that I was talking about is, are these approximations overestimates or underestimates? For this one, you're going to graph it to show us. I'm not going to ask you to do this on the exam for the overestimates or underestimate part. But for here, how they determine whether it's an overestimate is, if you have a curve and it's like so, and you have the tangent line above it, then that means that every value on the tangent line will be bigger than the value on the actual curve. So in that case, there will be an overestimate. On the other hand, if you have a curve which is like so, and then the tangent line is like this, then the tangent line lies below the function. So that means that every value that you approximate the f of s using the tangent line with will be what? Underestimate. But here they will just illustrate this using a graph. I'm not going to ask you to graph. You're not at graphing yet. You'll get there in 4.5 or so. Yeah. So that's just the notes. First, find the linearization. And then after getting the linearization, note that the original function, right, is approximately equal to the linearization. When x is near 1, please, as I said, the farther away you get from the point of tangency, the worse your approximation will be, right? So this is quite close, right? So we got 1.995. And then for this one too, you just find your x, which is 1.05, you get 2.0125. Okay, yeah. So this is the overestimate thing I was talking about, or underestimate I was talking about. As you can see, in this case, for the question that we are given, the square root of s plus 3 is a blue line, which is below the tangent line, right? It is always below. That means that if you want to find the value on this function and then use the tangent line to approximate it, the value on the tangent line will be bigger than what? That on the original function. So in that case, those numbers that we got are what? Overestimate. Please, are you okay? Right, so in this case, they are overestimates. Now, let me show you the underestimate case. So underestimate, either the curve is like this, and then the tangent line is, say, like this. Then in that case, every value that you use a tangent line to approximate will be below the function. So in that case, they'll be what? Underestimates. So that's how you tell. Well, one other way is you could use your calculator to get the actual value and compare it to the estimate, but yeah. Okay, please, any questions here? Anybody needs time? Okay. Okay, so this one is just saying that this is a good approximation, right? And then we know that these are overestimated because the tangent line lies above the curve, right? Now, a calculator gives us this, but the linear approximation gives an approximation over an entire interval. Yeah, okay. So now let's just a table showing us the linearization, the linear approximation, and the actual value. So as you can see, if we have, so it's still based on the same preamble, the square root of s plus 3, right, as our function. And then the linearization given by the 7 over 4 x over 4, right? So for that one, if a square root of 3.9, the x is what? 0.9, and the linearization is 1.975. You see the actual value is this, and this is very, very close, right? To 3 decimal places, they are the same, right? But these are still overestimates. The same with this. Now, one important thing you have to note here is at the point of tangency, right? At the point of tangency, they are the same, right? The linearization is 2, the actual value is 2, because at the point of tangency, they touch, right? They touch. At the point of tangency, they touch. So they will give you the same values. Now, one other thing that you have to note here is the closer you are to the point of tangency, the better your approximation is. And then the farther you go, the worse your approximation will be, right? So as you can see, since there's a point of tangency here, right, at the square root of 4, this one, then you notice that as you get farther and farther away, the approximation worsens, right? The closer you are to this, the point of tangency, the better your approximation is. Okay, and that's all on this. Please, any questions here? Anybody needs time here? Okay. Okay, so notice this table that the tangent line gives good estimates. Okay, and then it's still saying that it deteriorates when x is far away from 1, which is the point of tangency, right? If you move farther and farther away, it deteriorates, right? Okay, now that's all on the linear approximations. As I said, for your exam, please prepare up to linear approximation. I'm not going to ask you to overestimate, to find whether it's an overestimate or underestimate. I'm just going to ask you to first find a linearization and then get an approximation. So something like this. First find the linearization. As I said, it's nothing new. It's just the equation of the tangent line, right? And then the y is replaced with L of x. And then after finding the linearization, I'll ask you to approximate. So you just have to figure out your x and plug it in there, and that's all. Now let's move on to differentials. So for differentials, the idea of linear approximation, from this side, you're not going to be tested. From this side, you're not going to be tested on the exam. So the ideas of linear approximations are formulating the terminology of differentials, right? So suppose you have y equal to f of x, right? Then this dx, right, which we've encountered before, is something we call a differential, right? The x is a differential, the y is also a differential, right? Now, because if we have y equal to f of x, then dy over dx is equal to f prime of x. Then that means the differential y can be obtained as what? Just the derivative times what? This differential, the differential dx, right? So that's where this is stemming from. It's the usual differentiation that you do, but just that this time around, you see this as if it's like a variable, which you can multiply both sides by, right? So that's a differential. Now, this dy over dx is a derivative, so that's the difference. This is a derivative, and then these are differentials. So that's the difference between a derivative and a differential. Dx is a differential, dy is a differential. Okay, so don't forget that the y is the dependent variable. So that means that if we have the differential dy, then it's also dependent, right? And then the dy will depend on, because the solution for dy is dependent on the x and then the dx. That's why we are saying that the dy depends on the values of what? X and dx, right? Okay. So all that we'll be doing is we will find a numerical value for dx, and then we will use it to solve for dy, right? So let's look at the ideas from here. Recall that we said that the slope of the tangent line is given by what? The derivative. So more or less, it's as if the slope of the tangent line is dy over dx, right? And then evaluated at a point, right? Now, the slope of any line is given by rise over run. Now, what that means is, suppose you have a blue curve, right? The blue curve here. For that one, if you want to look at the change, like the change in the blue curve, right? So you're considering the point P here, and then a point here, the point Q. So between the curve, right, the actual curve, you see that if you want the change in the y, then that one, the actual change is given by delta y. But the change in y is from here to here. Now, it turns out that if you have the tangent line at this point, right, then the tangent line also has the dy, which is a rise, which is close to the actual change in the y. Right? Dy is, since this is rise over run, we can say the rise is dy and then the run is dx. Right? The rise is dy and then the run is dx. Right? So the rise in the actual tangent line, which is from here to here, is very, very close to the actual change in the rise in the actual function, right? Which is delta y. So that means that we are going to be able to use the dy to what? Approximate the values on the delta y. That's the idea, because they are very, very close. You see, delta y is from here to here, and then the dy is from here to here. They are quite close. So near the point of tangency, you see that as you get closer, say you get it close here, then the change, the delta y is say from here to here, the dy will be say from here to here, right? So this distance is quite close as you get closer and closer to the point of tangency, right? So that's differentials. So for differentials, we are going to use the differentials to approximate the actual change, right? The actual change in the function, right? So that's the idea here. Okay, so let's look at this. Now, the actual change in the function, right? If the function changes from, say, x to x plus delta x, then the actual change is given by what? The function evaluated at the x plus delta x minus the original function, right, at x, right? So that'll give you the delta y, which is the actual change. Now, sometimes it's difficult to find this, to calculate this, or it could be tedious. But in that case, similar to what we did for linear approximations, you can use the differentials to approximate the actual change, So for this one, let's just get on. I think an example will make more sense. So let's look at example 3. Right, let's look at example 3. The solutions are here. So let me move to the whiteboard, and then you understand what we are doing here. So example 3, this on differentials. Example 3 on slides. This 3.10. Section 3.10. Let me add it. Okay, so for this one, right, for example 3, we are asked to compare. So let me go back to the white. Compare the values of the actual change in the function. You see the actual change and the differential if the function is given by s cubed plus s squared minus 2s plus 1. And then we are saying s changes from 2 to 2.05, and then b from 2 to 2.01. So let's look at the a, right? So here we are going to compare them, and you will see that they are quite close. So the differential approximates the actual change very, very well. Okay, so now let me just go to the whiteboard. So the function is given by f of x equal to s cubed plus s squared minus 2s plus 1. And you're saying s changes from what? S changes a from 2 to 2.05. So if the function changes from 2 to what? Sorry, if the s changes from 2 to 2.05, then the actual function, what will be the change in the actual function? So let's call that, so this is the same as y. So we call that delta y. So delta y will just be the function evaluated at 2.05 minus the function evaluated at 2. That's all, right? So for this one, you're going to have f of 2.05 to be equal to what? So that's 2.05 all cubed plus 2.05 all squared minus 2 times what? 2.05 and then plus 1. And this is going to give us, let me look at the answer and write it down. So that's 9.7176. So that's 9.7176 and then 25. Okay. Now, after getting this, let's get a f of 2. F of 2 will be equal to what? So that'll be 2 cubed plus 2 squared minus 2 times 2 plus 1. And then that one is going to give us 9. So if you want the actual change in the original function, then it's just going to be what? This 9.717625 minus 9. And that's just going to give us 0.717625. Now, for this case, we are able to compute the actual change. But for some cases, for some functions, it may be difficult or impossible to compute this actual change. That's why the differential becomes very, very important. So let's just try and establish the fact that the differential approximation will be very, very close to this delta y. So let's now use differentials, right? So for this case, let's use differentials. So, or maybe let me do it for the b. Let me do it for the b, so that when we are done, we can compare the two, right? So the b is changing from 2 to 2.01. So let's do this one also. So for this one, the actual change will be f of 2.01 and then minus f of 2. So f of 2.01, the actual change, so that one will be 2.01 cubed and then plus what? 2.01 squared. And then minus 2 times 2.01 and then plus 1. So that one is going to give us, let me check the answer here. That one is going to give us 9.14. So that's 9.14140701. Okay, so we have this, right? Now, if you want, the f of 2 is already done, right? We did that in the previous step. That one is 9. So if you want the actual change, that is going to be 9.140701 minus 9. So that'll give us 0.140701. Okay, so this represents the actual change, but let's use the differentials to approximate, right? Using differential. Let's see if the differentials will be close to their values. Okay, so for A, from 2 to 2.05. Okay, so for that one, the first thing we have to do is, I'll have to move on to the next slide. So please do let me know if you need more time here. Okay, so let's get the function here. So the function is given by, so you have y equal to what? S cubed plus s squared. I think minus 2x, yeah, minus 2s plus 1. Let's use the differentials now, minus 2s plus 1. So for the differentials, just first find the derivative, like the usual derivative. So that one gives us 3s squared plus 2x minus 2, right? So if we want the differential y, then it's just going to be what? 3s squared plus 2x minus 2, all times what? Dx. Okay, so now let's just get the values and then plug them in, right? So we know that s changes from where? From 2 to 2.05. So the x is what? X is 2, right? Now, because it changes from 2 to 2.05 to, so x is equal to 2. Because it's changing from 2 to 2.05, we have the delta x, which is the same as the differential dx, to be equal to what? 2.05 minus 2. So that means this dx is what? 0.05, right? It's just the change in the x. Okay, now that you have this, you can get a differential. So dy will be equal to what? So that'd be 3 s squared. So that's 2 squared plus 2 times 2 minus 2. And then times what? The differential dx. So that's 0.5. And that'll give you what? That'll give you, give me a sec. That'll give you 0.7. 0.7. And as you can see, this 0.7, let's go back to the actual change, right? What was the actual change? It was this. You see, it was 0.717625. And this 0.7 is quite close to this number. You see? So that means that the dy is a good approximation for the actual change. For the B2, we are changing from 2 to 2.01, right? So your x is still 2. Your delta x, which is the true change in the y, is the same as the differential, and that one is 2.01 minus 2. So that's 0.01. So now that you have this, you know that the differential is given by dy is what? 3s squared plus 2x minus 2. And then dx. So let's get the differential. So that'll be 3 times what? 2 squared plus 2 times 2 minus 2. And then the differential dx is just 0.01. So do this computation and you get dy to be equal to, give me a sec, let me check it out. 0.14. 0.14. And as you can see, this 0.14, let's go to the true change. The true change was, where was it? Yeah, you see it was 0.140701. And this 0.14 is quite close to this. So that's the use of the differentials to approximate. Okay. So let me just go back to the PowerPoint and then I'll end here, right? I'll end here. And please, let me see. Let me just go back to the PowerPoint. Let me slide through. Yeah, let me slide through. So that I know where we are. So we're done with this one. Differentials. Okay, yeah. So the next time we will just use this differential to compute this. This will be the last example. Yeah. Then that'll be it. Okay, so a word on the exam. So as you know, I won't see you guys on Wednesday. I'm done with today. So we'll move on. You continue from here. Final example 4. Next time we meet. You just do this example and that'll be it. So regarding the exam, please be on time. I posted all the study guide material. If you don't understand anything, feel free to reach out. As you know, I won't see you again until Friday, right? Officially. So if you need help, please feel free to reach out, right? You can also talk to your TAs. Math Center also have a review. So that'll be all for today, right? Let me know if you have any issues, any questions or concerns. Yeah, that's all. Thank you for your time.
Thank you.
You're welcome. Yeah, the exam is 3.1 to 3.10. I'm not going to test you on differential. I'm going to test you on the linear approximations. You see, up to the linear approximation. So everything before it. And on the exam, you're not allowed a formula sheet. So you should have you should have memorized all the rules by now. You see, all the differentiation rules. Yeah. You're welcome. You're welcome. You're welcome.